problem. I have you at 251. Go for it.
So we discussed Greenberg's paper, authoritative sources in hyperlink diagram. So this is very similar to PageRank in the sense that it extracts information from the hyperlink structure. It treats the web as a graph, and it's kind of it was actually released around the same year. So there are, I think, two papers by Brin and Page that are relevant. So this cites the earlier one, and it's similar to Brin and Page's paper in the sense that it's iterative and based on the link structures, but it differs in the sense that it's query dependent, which means that this is processed at runtime instead of Brin and Page, where they computed an index and maintain. And it computes two scores, hub and authority score, as opposed to Brin and Page's PageRank score. And Brin and Page index, they process the whole World Wide Web corpus. But Kleinberg's paper reduces the whole World Wide Web corpus into a focused subgraph, into a subset on which they do the process. And the value of an inlink. So let's say page S links to page D. So Kleinberg's paper treats it as it depends on the outlinks from D, like where do the outlinks from the page D goes. Whereas Brin's paper focuses on where do the inlinks to page S comes from. So these are two slightly different views on the paper, on the problem of relevance and ranking. So we have covered most of it in class, the basic idea of it, that is to create a focused subgraph, to compute the hub and authority score, and to filter out. That is we'll be looking at that. And the extended ideas are how to compute similar page queries and non-principal eigenvectors, which I will come to. So we know that these common problems that plague the web, that is the scale and how unorganized it is, and there's no objectivity in defining what relevance is. It's different to different people, and there's no endogenous measure. By endogenous, I mean just by looking at a page, you cannot tell whether it's relevant or not. So you have to look at the structure around it, the pages that link to it and from it, and the query structure as well. We could have very specific queries that have a lot to do, like this Netscape support. So that's a scarcity problem. How do we find those small pages that can answer that specific query? And those broad topic queries, or I want to know about the Java programming language, and that's an abundance problem. And similar page queries. I want to find pages similar to Java, etc. So these are the three problems that the paper addresses. So links are encode a considerable amount of human judgment, in the sense that if page P links to page Q, it's an endorsement that, from P to Q. So that is a graph. Those two are, we can view each page as a node and the graph as the hyperlink as an edge. So it's a directed graph. So links to each and every link mean an authority or confer of a vote? No. It could also be for navigation, like on the nav bar, home, about. So we have a difficult, in finding the criteria between various, whether it's an authoritative link or whether it's a navigational link. And if you see Yahoo, it's a very popular directory. Everyone links to it. Is it popular? Really? Is it an authoritative source of information? So we view the graph like this. So the hubs point to authorities, and the authorities are pointed to by the hubs. So the authorities are authorities of certain information. So since this is processed at query time, we'd like to constrict the size of the subgraph that we'd like to perform the computation on. So we have S sigma for pages with the following properties, such that it's small, rich in relevant pages, and it has most of the strongest authorities.
That looks like so. I couldn't tell where I noticed the sigma. Good.
So this is the algorithm. So start with a root set generated using text search. So at this point, we don't use links, the link structure. We actually use the text-based search, where we go through each page and we find out whether it's relevant just based on the text alone, right? And then we add all the pages that link to that page and all the outlinks of that page. So if there's a page that is relevant, then we take all the pages that it points to and all the pages that point to it, and we add it into the root set. So we have certain problems as well. So there are some pages that have too many pages pointing to them, so we take only a certain number of pages. We can restrict that to D. But there are some links that exist purely for navigational purposes, as I said. So what we do is we remove all the pages that link within the same website, for example, within the same domain. And we retain the transverse links that go cross-domain. And there are links conferring advertisement or endorsement. For example, in my page I have powered by Twitter Bootstrap. I don't confer authority on that, right? So powered by WordPress, for example. So you have a parameter that limits the number of links to a page from within a single domain. So if you go to a domain and it says powered by Joomla on all the pages, then each and every page links to Joomla. So, but we don't allow that because only 4 to 8 links can go to a page from within a single domain. So these are how the paper solves these problems. So what we do is, this is the entire corpus that's given outside. So we constrict that to a root set, and we expand that into a base set by adding all the links that go to and from the page. So what are hubs? Hubs are the pages that link to multiple authority pages. So they are like indexes. So, and these pages pull together the authority pages, and they have a large out degree to authority pages. So this is here is an iterative algorithm. So we give each page an authority weight and a hub weight. We start at 1. And if P points to many pages, so if the I operation updates such that the hub score of a page is equal to the authority score of the pages it points to, and the authority score is equal to the hub score of the pages it gets links from. So it's kind of mutually recursive. So the hub score is the authority score and is computed from the authority score, and the authority score is computed from the hub score. So Kleinberg's paper also proves that this converges, because there is an issue whether this converges, and Kleinberg's paper does prove that, and in around 20 iterations. So, and then we take the top few authority pages as the top results and present it to the user. There's another problem here. Yahoo, for example, would have a lot of popular pages with a large in degree. So the solution is that these authorities must have considerable overlap in the hubs that support them. So the hubs that support authorities must be similar. And in comparison to Alta Vista at that time was a completely text-based search engine. So this gave a much more relevant ranking results for many such pages where the text was not rich. The text did not provide much content or relevance just by if you don't process the link structure. So coming to the problem of similar page queries, how do you find a page similar to P? It's just the only difference is the root set initialization. Instead of saying find T pages containing the string sigma, we say local to P, what are the strongest authorities? So the find T pages that point to P and find the authorities that it points to. So that's a very simple initialization, and the rest of the algorithm is the same. We're computing the hub and authority score. So if P is a highly referenced page, then there's an abundance problem. That we have too much text to work on. So too much pages to work on. So the solution is to restrict it to the local region. Maybe say you have a maximum separation of say 3, and the localized algorithm gives better results than just in degree ranking. And one problem was there is this notion of competitive and cooperative nature, where competitive means pages that compete. For example, Toyota and Honda would be competing with GM, and cooperative pages could be like, say, resulting from a common cause. Like Honda would be Acura because both of them are under the same brand, for example. So this also would probably support a competitive nature more than cooperative. So there's a slight bias. That's my personal opinion on this part. So related work, we have social networks standing. So social networks and Facebook's EdgeRank is somewhat similar. It's about a number of friends I'm connected to, a number of friends who connect to me, and Facebook's is more or less an an undirected graph, except for pages, but we see Twitter and Google Plus, which operates on more of a directed graph principle. Then we have the scientific citations, which is a big study. It's called bibliometrics. So we have like Garfield impact factor. Some of them only compute the inlinks, and they don't care about the outlinks. And the hypertext and World Wide Web rankings, index node and reference node. So index nodes are somewhat like hubs, and reference nodes are somewhat like authorities. So, and we have other link-based approaches to World Wide Web that basically deal with the text around the anchor text around, and clustering of link structures. The clustering is a very different problem to finding hubs and authorities scores. So we have another problem here, that is the query string may have different meanings. Suppose I give jaguar, it could mean the animal or the car. And so what we do with that is non-principal eigenvectors. What we do is compute the authorities, and we find clusters of authorities. So we find the topmost authority cluster, we remove that from the subgraph and recompute. So in that sense, we find all the multiple authority clusters that can be found. And randomized algorithms, so we have multiple technical communities that have different notions. So this can be computed in the same way as the previous one. And if many people, there are some polarizing issues, for example, like abortion, which two groups have very opposing or polarized views on. So, and these people are not likely to link to one another. So how do you find the hubs and authorities in such a competitive environment when people don't link to each other? And clusters bring in abundance problem. What scatter gather is you scatter the pages to users such that you present users with various hubs, right? Like various clusters that you found from hubs. And the user selects, I want this cluster. For example, Jaguar. If a user searches for Jaguar, then you can say, did you mean the animal or did you mean the car? So the user says the animal, and that would be an example of a scatter gather. So an eigenvector is the densely linked collection of hubs and authorities in the graph, and it's calculated by iterations. And this is exactly what I said. So we have more examples: Jaguar, the car, cat, Atari. And I'll come to this. So we have ASP, adjacency matrix of the graph, and these are the update operations. That is, these are self-mutual. So we have the update operations that perform the authority update and the hub update, and this is the authority update, and this is the hub update. So they are performed iteratively, and Klingberg proves that this converges, and the conversion limits are the principal eigenvectors. That is, the top authority scores are the eigenvectors. So in the previous page,
Anyway, just to let you know, you're kind of getting to that point where the other person, I mean, like around 15 minutes. So.
Okay.
Yeah.
So here we remove the principal eigenvectors and go to the non-principal eigenvectors for the subsequent users. So sometimes we have pages. Suppose you search for a very specific query, the broad pages wins out because it has more links pointing to it. And this is actually, Klingberg says that this is not a problem because it abstracts a simple query to a much broader one, and people can still follow the links and go to the very specific query. And the evaluation is based on human judgment, and so the anchor text to weight individual are links. That is the evaluation was performed with more heuristics than just what Klingberg provided. Klingberg did not talk about the anchor text, but the evaluation was done with anchor text. Clever, the user survey was done between Clever, Yahoo, and AltaVista. 31% of the users said that they are Clever and Yahoo are similar. 50% said Clever is better, and REST 19 said Yahoo's better. AltaVista is just a text-based search engine, and it wasn't very popular compared to Yahoo or Clever. I mean, users preferred Yahoo over AltaVista. And so, to conclude, the paper goes just beyond relevance and ranking. It wants the authoritative sources of information, and a global notion is input without maintaining an index of the so we don't maintain an index of the World Wide Web. And we also find interesting patterns of how the world is socially, the bow tie shape of the web. So the results are good, but there are some topic drifts that occur because of a lot of popularity of certain pages, and the CleanWorks algorithm uses only the top authority scores, but they might be more useful pages among the hubs, and there's no way to incorporate user feedback. There were some improvements made by using a support vector machine by Greg Nielsen, and by Bharat. It's one more. Here the pages are not weighted, so the Bharat weighted each page while taking into account. They weighted each page while taking into the expansion, creating the focus of that. So these are the improvements that were made.
Excellent. All right, I have questions, but I'll open it up to others first. Oh, all right. Well, now here it comes. So great job. Few things. 20 iterations seems really arbitrary. I mean, it's a nice, even number.
It's the average number of iterations that it converged upon.
Yeah.
That was experimental.
No, I get that. I'm just saying, it just seems really arbitrary to me. I mean, do you have any insight? I mean, is it based on the data? You know, that he was, and this might not have been in the paper. I might be asking you something beyond
Sure.
that.
It wasn't in the paper, but I'm not aware of the time exactly that this was performed in. It could possibly be to do with just the size of the relevant pages that one could.
Because I think he's about 5,000 or something like that. Like, you know, so maybe, I mean, I don't know, 20 doesn't really go into 5,000. I mean, so I was trying to just figure out the relationship between those. So.
Okay. And I really don't have an insight on how the tracking came, but
It's absolutely not a trick. I mean, it's not a. There's not a right or wrong answer to this question. I was just wondering.
But if it was my intuition, I'd say because it was probably due to the small size of the World Wide Web at the time.
So that leads to my second question. Can you go to not your last slide, but like a couple before then? Yeah, stop there. Perfect. Yeah. So you say a global notion of structure is inferred without directly maintaining an index of the World Wide Web or its link structure. They do maintain. You do need the link structure, though, right? Like, so for example, in Nudge, you know, I've got an implementation of HITS right now that's experimental that one of my 572 students did 2 or 3 summers ago, and it takes the web graph as input. So, like, did you mean there that without requiring an index of the whole web? Yeah. Okay, that makes sense.
So there's a minimalistic link structure that is indexed, but the whole World Wide Web is not necessarily indexed. But it's very query dependent, so it's not very easy to scale this algorithm up. So it's not very popularly used today.
A lot of it is used offline, and so yeah. So and then in your related stuff to class, I didn't see your mention of Nudge. I've been talking to you about it. I'm just kidding. All right, so relax, stop. Thank you. All right, so last talk of the day, and there's 20 minutes left entirely in class, so if you finished in 15, that would be great, because that will leave the next class 5 minutes. This is good abandonment in mobile and PC internet search.